So yes, let's get started. And thank you, Jonathan, for giving us this talk on massive stars. So just a quick introduction. Jonathan has actually been an integral part of CDY from the very beginning. He studied physics and applied math at NUI Galway in Ireland, and received a master's thesis at the Harvard-Smithsonian Center for Astrophysics. He completed his PhD at the Dublin Institute of Advanced Studies, working on computational studies of H2 regions around massive stars. He then spent 5 years working as a postdoctoral researcher in Germany, and he was an Alexander von Humboldt Fellow at the University of Bonn and at the University of Cologne, where he was working on stellar winds and supernovae. He was then awarded a Royal Swedish SFI University Research Fellowship to establish a research group at DIS to investigate massive stars in the interstellar medium, focusing on hot X-ray emitting plasmas and high energy processes. He's also the convener of the working group on stellar sources in Hesse, and he serves on the organization committee of IAU Commission, Computational Astrophysics. So welcome, Jonathan, and thank you again. And please get started. And I'm just going to ask people to mute if they're not speaking.
Okay. Yeah, thanks very much, Rashmi. And thanks very much for the invitation to speak today. So let's see. Hopefully you can see the screen okay.
Looks great. Looks great.
Good. Yeah, so I'm going to talk about massive stars at high energy. And so as Rashmi said in the introduction, so a lot of my research has actually been on much lower energy processes than what most of these talks have been about. So like thermal X-ray emitting plasmas, and it's only in the last few years that I've started to work on higher energy processes. So I will have a bit of both in the talk. So this is an outline. In some ways, it's going to be a very broad talk. So I'm going to start talking about stellar wind bubbles, and particularly bow-shocks around runaway stars. Then I will discuss colliding wind binary systems, and then going from sort of small scales to bigger scales, then the combined winds, winds and supernovae in star clusters, and the recent observations in this area. And then I will finish by talking about dead stars. So basically high mass X-ray binaries, where one of the stars is now a compact object, novae, where one of the stars is a white dwarf, or supernovae interacting with stellar winds, where one of the stars has just exploded in the last year or so. And then quick summary. And apologize in advance that most of the observational results I'll talk about in high energy will be very biased towards the Hess results, especially from the stellar sources and the supernova remnants. And nobody can quite remember what the 2Ps stand for. Pulsar wind nebulae, I think, and something else, working groups. So most of you probably know this, but this is the Hess experiment in Namibia, which I got to go and see last year for the 20th anniversary meeting. It was really cool to be there. And it's amazing how big the big telescope is. I mean, the small telescopes are pretty big, 12-meter diameter, but the big one, 28-meter, it's really quite overwhelming to be standing beside it. And so what's cool about Hess is that it is the only Cherenkov telescope in the southern hemisphere. So there's a lot of things that only Hess can see, and until about 2028 or so, that will remain that way until CTA South gets built. All right, so getting into stellar winds. So the topic is from massive stars. So we start with stellar winds. I really love this picture of the Rosette Nebula around this nebula NGC 2244, or I mean the star cluster NGC 2244. This was observed so many years ago, and already in 1966, Matthews suggested that this cavity that you can see at the center here was maintained by the basically fast stellar winds of the early type stars that you can see here in the center. Models of this were developed, for example, Dyson and de Vries, 1972, And then this Weaver-McRae et al. 1977 models basically like this. So you have a wind from the star, and then at some point, the pressure of the interstellar medium equals the ram pressure of the wind, and then you get a shock forming. So this is the wind termination shock. You have a contact discontinuity separating the wind material from the interstellar material, and then quite often you have an outer shock as well from the expanding, swept up interstellar gas. And we see this again and again, also binary systems, star clusters, these two shock structure with the contact discontinuity in between. And obviously, if the star is moving, then the pressure, the external pressure will be anisotropic. So this bubble will be distorted. And in an extreme case, then this will become a bow shock if the star is moving supersonically. So this is an example of a bow shock, what you can see on the right here. This is CDY-Yuki. It's actually the nearest O star to Earth. It's only 135 parsecs away. And it makes this fantastic bow shock seen with the Spitzer Space Telescope. And you can just about to see some diffuse X-ray emission from the hot stellar wind bubble in here. It's quite easy to calculate the size, just basically simple fluid dynamics and pressure balance. Basically, stars with strong winds, so high mass loss rate, high wind velocity, will drive large bubbles. If you have a denser interstellar medium or the star is moving faster, then the bubble gets compressed, it will be smaller. So this is what the bubble looks like in the case of a bow shock. It's basically a distorted version of this plot from the Weaver paper. So here are three examples of bow shocks. On the left, you have this famous bubble nebula, NGC 76335. And you can see out here, I think there's a nitrogen-2 emission. There's this this is a shock because the star is actually moving this way towards the top left at about 30 kilometers a second. It's moving in quite a dense medium, which is why it's so bright in optical emission, you see here. Most of them are seen in infrared. So this is CDY-Yuki again. And this is BD plus 43, 3654, which is like a 60 or 70 solar mass star that's got ejected from the Cygnus OB association. And it drives a very large bow shock. So this is the X-rays from the region. So this was the part of the PhD thesis of Sam Green, who you can see up here. This plot is from Toala et al. 2016 using Chandra observations. And Sam's job was to try and model this. So the contours show the infrared emission and the red shows the diffuse thermal X-ray emission of the stellar wind bubble. So we made some models of that. Basically, the first 3D MHD simulations of the bow shock. We calculated the synthetic X-ray emission that you see here, and then superposed synthetic X-ray emission on top of the infrared emission. We found that basically we can match the infrared emission pretty well, but the X-ray, we didn't do a great job on it, which I will explain why in a second. So to use this, or to model this, we're doing MHD. So it's non-relativistic, obviously, because these winds are a few thousand kilometers per second. And in this case, 3D Cartesian grid with nested grids to focus resolution here at the origin. So this is an example of one of the simulations that Sam did for his thesis. Here, the star is moving from left to right, and we're in a reference frame where the star is not moving on the grid, and it basically reaches a steady state after a while. And this is showing gas density, where the blue is low density, and this is the high density swept up interstellar medium, and this is the bow shock then out here. You can see this is nice and smooth, which impacted actually the X-rays that we found. So the X-ray emission that we got is too faint. This is a time evolution of the X-ray emission from the simulation. I guess just look at the blue lines. These are the this dashed line is from the whole simulation, and this is from just a smaller region around the star. And the gray was the observational limit here. Basically, the conclusion from this was that we didn't really resolve it well enough, because this is the Chandra image here. In the simulation, all of the emission we had was from up here. We had very little in the wake behind the star. So since then, we've been working on higher resolution simulations. It turns out if you just sort of double the resolution, then suddenly you start resolving all of these instabilities at the contact discontinuity. This gets you a lot of turbulent mixing in the wake behind the star. And this completely changes the X-ray emission that you get, actually. So this evolution of this one, so I'll speed it up a little bit, and you can see this Kelvin-Helmholtz instability developing, getting these waves forming. And so from this, we've calculated the synthetic X-ray emission. So this is what the synthetic X-ray emission looks like. So after the initial phase sort of settles down, and sometimes it's bright, sometimes it's faint, but basically the brightest emission is now from the wake behind the star, because we are resolving the turbulence. So what does this have to do with non-thermal processes? Not very much, except that if you want to model the non-thermal plasma, you need to understand the dynamics of the thermal plasma, and ideally the magnetic field structure of what you're modeling. We're working now on calculating synchrotron emission from simulations like this to compare with radio observations. And then moving forward with some post-processing, you can model then the high energy emission, which has been done already with 2D simulations. So we also, because nobody was really doing, well, there was one group that was working on this quite actively, but we decided we would try and observe these bow shocks in radio, see if we could detect them, because we predicted that they should be quite bright in thermal emission, if not in synchrotron emission as well. So this is the one in the Cygnus region, BD plus 43. This had been detected already in radio, and we got basically deeper and higher resolution observations. And these gray contours here show the emission that was detected with the VLA. And this here is the bubble nebula. So here again, we detected this part upstream region of the bow shock, and also a bright thermal emission from a cloud that's behind the bow shock. So we calculated the spectral index of both of these and got quite negative, like so minus 0.7 or so, which is typical of synchrotron emission. Indicates that basically the emission here is dominated by synchrotron, which is a little bit surprising. I'm still slightly suspicious of this result because it's done with an interferometer, and looking at faint diffuse emission with an interferometry is quite difficult to get an accurate spectral index from that, but this should be at least followed up. So this was the PhD thesis of Maria Mozzori, and you can find the paper here if you're interested in more about this. The first detection of the bow shocks in radio was by Paolo Bonaglia in this 2010 paper. And I'm showing a plot here from the paper, which was basically taking the radio observations and extrapolating wildly to see what you could possibly detect at higher resolution, or higher energy, I mean. So X-rays, gamma rays potentially. It turns out this was quite optimistic, or over-optimistic, possibly predicting like 10 to the 32 ergs per second at TeV gamma rays. Since then, there have been a few more observations of bow shocks in radio, mostly favoring non-thermal emission, but pretty much all with interferometers. So I think that still needs to be fully confirmed, but it seems reasonably solid by now. There are actually no detections in X-rays, which is somewhat expected when you look at this plot. Basically, the synchrotron emission cuts off at about 0.1 keV, and this should be basically for non-thermal emission, the absolute minimum in emissivity should be in the X-ray band of 1 to 10 keV, unfortunately. Also no detections in gamma rays. So there was a paper searching in Fermi-Lat 2014 with a lot of upper limits. And then in 2018, as part of the Galactic Plane Survey, TESS collaboration also published upper limits, basically at the level of 0.1 to 1% of the wind kinetic power. So in terms of the theoretical predictions, first paper I could find on this was Del Valle and Romero from 2012. This was actually quite optimistic, said the luminosity could be 10 to the 30 to 10 to the 34 ergs per second in gamma rays. More recent models, so this here is from Del Palacio et al. 2018, are more a bit more conservative. So at a level of like 10 to the 31 ergs per second, which unfortunately is out of the reach of Fermi, which you can see here is the gray line, and possibly out of reach of CDA as well. Here's the black line. And this is sort of a multi-zone analytic model with 4 different regions, and then following the advection with analytic prescriptions. In terms of then computer simulations, so Del Valle and Paul did this nice study of post-processing 2D simulations of a bow shock. Here the star is moving towards the top. Basically injecting electrons at the wind termination shock and letting them advext and diffuse according to a fairly simple prescription, and plotting basically how the bow shocks should look in radio and also in gamma rays. But in any case, the gamma ray emission is not really bright enough to detect, unfortunately. So just to quickly summarize this on bow shocks, the 3D simulations are pretty standard now. So you include the stellar and the ISM magnetic field. You have to make quite strong assumptions on the stellar field because there's usually very little observational data to go on. So predicting observables related to the thermal plasma is coming along quite well. So with some assumptions, you can model then the non-thermal electrons. But what they emit then, there's a significant uncertainty in terms of the magnetic field, because that we're seeing basically synchrotron emission. So the only evidence that we have is from radio measurements that there is non-thermal emission, that there's any non-thermal processes occurring at all. And as I said, the X-ray upper limits, you don't really expect to see anything anyway. But the gamma ray upper limits can already exclude the most optimistic theoretical scenarios. And I guess the problem with these sources is that the energy densities are pretty low. So the radiative processes are pretty efficient, so it's hard to observe. And the models show that basically all of the accelerated protons will just escape the system, and we'll never see any emission from that. I personally think so Zeta Ophiuchi may be the best candidate because it's so close. It's just unfortunate that it has a very weak wind, so 100 times weaker than some of the other sources, for example, in Cygnus. So this is probably not the most promising avenue for studying high energy processes in massive star winds. So moving on, colliding wind binary systems. Now we have 2 stars, not just one, and because the stars are close to each other, the shocks form at much higher density in the colliding winds. You also have short timescales, so you can see time variation. So here we can hope that the high energy emission will be much brighter. The difficulty is that the stars really have very strong radiation fields, and so the gamma-gamma absorption becomes a problem at high energy. So this is a sort of cartoon put on top of a 2D hydrodynamic simulation. In the colliding wind systems, typically you have an O star, which is the secondary star of the system. It has a relatively weak wind. It's quite a big star. And then a Wolf A star, which is the more evolved star, so it's burning helium, and it has a much stronger wind. And then you form this two-shock structure from the two winds, and the contact discontinuity at the center. And particle acceleration should happen through diffusive shock acceleration at the two shocks. And these are bright X-ray emitters, bright radio emitters. You can measure the gas temperature from the X-ray emission, the thermal X-ray emission, and you get like 100 million Kelvin or so. Depending on the system. This plot on the right-hand side shows an example of synchrotron emission from WR140, which is one of the archetypal colliding wind binaries. It's also in Cygnus. And these colored shapes here this is actual radio data put on top of a cartoon taken from different points in the orbit. And you can see basically this is the apex of this shocked region. It gets fainter as the stars move towards each other because close to periastron, the densities are so high that the synchrotron emission is absorbed by free absorption. But this follows pretty well what you would expect from just colliding winds, two shocks forming, and this sort of bow-shaped structure. So what's nice about the binary systems, as I said, is you have these predictable time-varying shock conditions. So you can do a lot of research on massive stars, on their winds, wind acceleration, wind clumping, things like that. Some of them also produce dust. So you can see in the bottom left, WR104. These are actually the most intense dust producers in the galaxy. There are not very many of them, so they don't dominate the dust budget, but each one individually is producing a huge amount of dust. This is a recent image from James Webb Space Telescope showing WR140, and this is dust that's produced during the periastron passage. And what you're seeing in these rings are successive periastron passages. So each one of these rings is it's about 7.9-year orbit, so like about 8 years apart in terms of wind travel time. And you can see there's like 16 rings or so here. This is an amazing image we use. So for WR140, we've observed it with X-rays pretty continuously for 3 periastron passages now. And it follows pretty much what you expect for this dashed line is the luminosity in X-rays that you expect for adiabatic shocks. Basically, the volume of the shocked region gets smaller as you go towards periastron, but the density increases. And because the X-ray emission scales as density squared, then the X-ray luminosity should scale as 1 over the separation of the stars. Follows that pretty closely, except there's this very sharp dip around periastron. And it's pretty certain that this is the transition from adiabatic to radiative shocks. So basically, the cooling timescale of the thermal plasma becomes shorter than the the escape time of the gas from the shock. And the hot plasma region then collapses into cold clumps. And this is also the time when the dust is produced in the orbit. So there have been simple models of this, and there have been some hydrodynamic models of this as well. If you want to model the thermal plasma, maybe you can get away with hydrodynamics, but actually, once the shocks become radiative, then the magnetic field compression can become quite important dynamically, and that can actually limit the compression you get, which can affect the thermal observables as well. But if you want to look at the non-thermal emission, you really need to know. So conditions in the thermal plasma, what are the shocks, what are their properties, and if you can, the magnetic field configuration. So what's the angle between the magnetic field and the shock as a function of well, the star and its orbit. And if you try and model these systems through the periastron, if you have phenomenological or one-zone models, these can be often well, inconclusive in the best case or inconsistent in the worst case. And so what we're trying to do is, first step, to do MHD simulations, and then with post-processing for cosmic rays in the test particle limit. So we're assuming acceleration is not very efficient, so no back reaction on the MHD flow. So this is a simulation that we did of WR140. This shows the computational grid. The actual simulation we did was higher resolution than this, but it's just so you can see basically focusing the resolution in on the periastral region. These are the orbits of the two stars on the grid. And so we started 140 days before periastron and finished about the same time after periastron. The two new things we added to this were MHD. So basically, nobody had included magnetic fields in this sort of simulation before, where you follow the orbits of the stars. And we included inverse Compton cooling. So, but inverse Compton cooling of the thermal electrons. I thought I had discovered this. Turns out that it was discovered in 1970s, and then also in 1993. But basically, nobody has included this in any modeling for the past 30 years, as far as I can see, which is really surprising. So we did an experiment, basically doing the same simulation with and without inverse Compton cooling of a O star. Well, this is the WR140 system, so this is the Wolf-Rayet A star, the O star. This one has got no inverse Compton cooling, and this does. And you can see basically this shocked region here it's not quite adiabatic, but it's also not strongly cooling and doesn't have runaway cooling producing instabilities, whereas in this case it does. And this follows exactly what you expect from analytic calculations. Basically, the inverse Compton cooling timescale depends only on the radiation energy density in the non-relativistic limit. So we did the simulation. As I said, this is a plot of the gas density in the orbital plane. And you can see just around periastron, the shocks become very unstable. This is because the shock region, the inverse Compton cooling makes the cooling timescale of the shock region shorter than the dynamical timescale, and it collapses to a thin sheet, which is dynamically unstable to this thin shell instability. And so you can ask, does this agree with the observations that you get? No, I added an extra slide to show to look at the alpha and Mach number of the flow, so that you can see what's going on around periastron. So this color scale shows the gas density here on a log scale, grams per cubic centimeter. And then these lines are lines of constant Mach number. So the pink contours are Mach number 20 to 70 in steps of 10, and the black ones are then 100 to 700, so in steps of 100. So you can see you're still deep in the acceleration zone of the wind of the O star, where the shocks are forming. And the post-shock region actually has a much lower Mach number compared to the well, these are actually the cool regions that have where the magnetic field is pretty strong, and so the Mach number is lower. Yeah. So we calculated what the X-ray emission should look like over time in the orbit. This is looking down on the orbital plane, which is not quite the view that we have from Earth, but it lets you see. So you have this nice smooth arc shape of emission, which then actually, so this is a zoomed in version. You can see once the shock breaks up, then the emission becomes much more broken up, and the region emitting X-ray, emitting X-rays is much smaller. So you can guess that the light curve shows quite a strong dip here around the periastron. So it turns out this is the case. This is the green line, the model with the inverse Compton cooling and wind acceleration. Compared to the observations, it's kind of qualitatively similar in that we get this really strong dip around periastron, and the light curve is then asymmetric around periastron. It's not broad enough. I would say we didn't actually tune the simulation at all to try and match the observations. There's a number of uncertain parameters that could broaden and deepen this dip, which we will look into in future work. This system is going to have periastron again in November of this year, so it's quite timely to be looking at this. And then the idea is then, because we have the magnetic field configuration, we know the angle between the magnetic field and the shock at all points in the simulation going through periastron. So we can then make some post-processing calculations to look at the shock acceleration and potential high energy radiation. We also tried looking at radio synchrotron emission. This was done by a bachelor student. It's not very useful yet in terms of predictions because it doesn't have the free absorption. But we'll put that in. And yeah. So moving on, what's motivating to do these FHD simulations is that, as I said, the hope of being able to do looking at some particle acceleration and high energy radiation processes. There are a lot of systems that have got bright radio synchrotron emission. This is actually used as initially it was used as a way of finding the colliding wind boundary systems, which ones are anomalously bright in radio with synchrotron emission. And there have been a lot of predictions over the years that basically seem quite promising for high energy radiation. Nevertheless, only two systems, so Gamma Velorum and Eta Carina, have been detected at gamma rays, either high energy or very high energy. So this plot here is from Guillaume Marty de Wese's paper in 2020 with the Fermi-Lat spectrum of Gamma Velorum, and his paper shows also some indication of orbital modulation of the system, which is important for conclusively identifying it with the binary system. Actually, it's pretty hard to detect, so the flux level is pretty low in Fermi, and if you extrapolate just this power law down, which is quite an optimistic scenario, down to TeV, then it's basically hard to even detect this with CTA South, let alone with Hess, which is, so this is a pretty faint gamma ray source considering how close it is. So it's only 300 parsecs away or so. It's about 5 times closer than most of the other binary systems that we observe, the high mass X-ray binaries. And so it seems that only Eta Carina is an efficient emitter. So Eta Carina it's basically the most extreme colliding wind binary in the galaxy. So it's got a 5.5-year period. It's got this LBV primary, and O-type star or Wolf-Rayet star is the secondary. It's not really clear. It has non-thermal and variable X-rays detected through periastron, and it was also detected quite early on by Agile and Fermi-Lat. And here you can see on the right-hand side, this is from the Hess paper in 2020, so showing results from the 2014 periastron passage. So these are the Fermi results, and these are the Hess results. And I mean, the system is a lot further than Gamma Velorum, but it's also a lot brighter in terms of the flux that we receive. So it's really hugely more luminous than Gamma Velorum. And then we also observed it in 2020. These results were presented at the ICRC last summer. So I show one plot from the ICRC presentation of 3 months time muscle. Here are the HESS results from CT5, which is the big telescope, getting down to lower energies, so 150 GeV or so. And these are the CT1 to 4 observations at higher energies. So we clearly detected it again. The analysis, I say it's a difficult analysis. I mean, it's a whole PhD worth of difficult analysis. Simon did a huge amount of work developing dedicated analysis methods to beat down the error bars, because the nebula is so bright that this night sky background is a real problem. So we found basically a soft spectrum continuing the Fermi-Lat component, and I mean, the error bars are quite big on the different flux points during periastron passage, but if you do a statistical analysis, there's no significant variability. So this paper should be coming out relatively soon. If you're interested in more information, I guess you can go and look at the ICRC proceedings. So going to summarize the colliding wind binaries. It's kind of surprising to me that 3D MHD simulations haven't been investigated in more detail before, considering the non-thermal emission that's there. So we're doing quite a bit of work on that at the moment. Mainly at the moment to model the thermal plasma, but also in future to extend this to look at particle acceleration. I think it's a surprise that only 2 systems have been detected at high energy and only 1 at very high energy. Both interpreted as hadronic emission. So for gamma velorum, it's been argued that actually the electrons can only reach 100 MeV, and that the hadronic emission should be absorbed at greater than 100 GeV. So it may be very difficult to, there could be a very strong cutoff there. So we may never observe this, even with the successor to CTA South. For Eta Carina, it's also hadronic, so this means that there should be efficient acceleration of protons to 20 TeV or above at least. And the gamma-gamma absorption is actually ineffective in this system. So what about other systems? There are really a lot of these colliding wind binary systems. Some of them a bit closer than Eta Car, some of them a bit further. The other one that people hoped would be bright, this newly discovered system APEP, which is a double Wolf-Rayet system. This was not detected with Fermi, and Marty DeVes et al. Basically argued that even though this is the brightest radio synchrotron emitter of all the colliding wind binaries, if this was a predictor of the high energy emission, they should have observed it. I think WR140 could actually be a good target for TeV emission, although it was also not detected by Fermi, so it can't be that bright. It is in the Cygnus region, which maybe makes things a bit confusing, but it's not in the center of the Cygnus emitting region. And from what I could see, it's only been observed by Veritas for 2 hours, so I think this could be interesting to look at later this year. So moving on, star clusters, almost the last part of the talk, apart from the postscript on dead stars. So here, basically you have a lot of sources, and the colliding winds of all these stars produce multiple shocks and within a larger volume. So this means, in theory, the cosmic rays can be confined longer and get to higher energies. This is one of my favorite astronomy plot images. This is NGC 3603, taken with Hubble Space Telescope. Here you can see all the massive stars. And this is the molecular cloud that they formed out of here to the right. And you can see very sharp contact discontinuity here between the very low density stellar wind material and the high density photoionized H2 region. So it's been thought for a long time that these star clusters could contribute to cosmic rays and what we see in the gamma ray sky. For example, this old paper from 1983 by Cesarski and Monmerl. This is a classic paper. So recently, there's been a lot of activity in this field. Aharonian et al. 2019 looked at Fermi emission from clusters and associations, arguing that these are continuous cosmic ray producers and contributing quite a bit, especially at the highest energies. I wanted to mention also this paper by Morlino et al. 2021, which suggests that you could have efficient particle acceleration in the termination shock of the cluster wind. The idea being that all of these winds collide, produce a hot plasma, which expands out at approximately the sound speed, say 1,000 kilometers a second. And this should then produce a second shock, so a termination shock outside here if you have a sort of the beginnings of a superbubble forming. Also, these models by Vieux et al. In 2022 and 2023, showing that in theory you can get really very high energy particles. And then when I was preparing the talk, I found this very recent paper by Perron et al. 2024, so it's just published, detecting actually embedded star clusters, so very young star clusters in the first million years of their life with Fermi-Lat. And this argues basically that stellar winds should make a significant contribution to the cosmic ray population at the highest energies. So there are two questions. So one, what's the contribution of stellar winds to the cosmic ray population? And two, what's the contribution of star clusters? I mean, the answer to two should be that they are quite important, because star formation is clustered. Most massive stars form in clusters. So the majority of supernovae should also be in clusters. So if supernovae are a contributor to cosmic rays, then we should see this in star clusters. But whether the stellar winds are or not, this is a very active field of research. So I wanted to mention a couple of results on this. It's not something that I've done a huge amount of work on. So Westerland 1, this was a bright TeV source detected, published by the HESS collaboration in 2012. And then again, a detailed analysis in 2022, which we may hear more from in a future talk from Lars. So I'm showing here the HESS flux map. This star is the position of Westerland 1, and here are 2 pulsars, and you can see this bright shell of emission around Westerland 1. It's about 1 to 2 degree diameter. It's a bit offset from Westerland 1. And what's interesting, there's no energy dependent morphology, and it has a hard spectrum that extends to tens of TeV. So in the HESS paper, we looked at hadronic and leptonic models. In theory, both of them work. But if there is a cluster termination shock that coincides with this shell, then the leptonic model is very attractive. And if you do some calculations, it should be at about this radius. So where did the cosmic rays come from? Well, and this is a complicated question, because Westerland 1, depending on what its age is, it likely had quite a lot of supernovae, and some estimates up to 100 supernovae in the last couple of million years. That's probably a bit of an overestimate, but it certainly had a few supernovae. And it also has the richest galactic population of Wolf-Rayet stars, so the wind kinetic power is very high. So I don't think we can answer the question, basically, of what's doing the acceleration in this system. Westerland 2 is an interesting case. It's a younger star system than Westerland 1, so it's not clear if it had any supernova explosions yet. Showing this nice plot from this paper by Povich et al. 2008, where you see these bow shocks. That's from out here. Here's one here, here's one here. These bow shocks point back towards the star cluster. So what that tells you is that there is a wind coming from the star cluster, and this massive star is embedded in this cluster wind, and that's what's producing this bow shock. This indicates that actually there is a wind about 300 kilometers a second moving out of Westerland 2, going past this star. So this is some evidence that there actually is a cluster wind from the system. And there is a bright TeV source associated with Westerland 2. And also for this, there were results presented at the ICRC by Tim Lucas Hodge. So I show one plot from his presentation. This is the TeV map with Hess. The star is again the position of Westerland 2. This is the TeV emission, and you can see there are multiple components, and this is the main component here. So the emission extends all the way up to a few tens of TeV with a power law. Maybe there's a cutoff. I'm not sure if it's really very strongly constrained by the data. So there should be a new publication on this coming out quite soon. Then the last cluster, R136. So it's the central cluster of the Tarantula Nebula. It's the most massive star forming region in the local group, and with the most massive stars that we've ever seen. So this was presented by Lars Moorman at TEPA. We detected TeV gamma rays from the region. I'll show you this is from the TEPA presentation. So this is the map that we have. If you then subtract the emission from N157b, which is Pulsar Wind Nebula, you see 30 Dorada C, and you also see this emission from R136, which is a really nice result. Seems to be spatially extended, so it's more luminous than Westerland 1, for example. And again, there will be a paper coming out in the next few months on this. So very nice result again. So summarizing this, I mean, this is a really exciting field in gamma ray astronomy. Star clusters obviously are effective accelerators to hundreds of TeV probably. If this is hadronic emission, at least we've shown that. The brightest objects have had a lot of supernovae in the last few million years. So actually the youngest clusters are key for testing this. And I suggest you look at this paper, which suggests that actually the youngest clusters do effectively accelerate particles through the stellar winds. So I see I'm actually already at about 45 minutes. Do I have time to spend 5 minutes talking about dead stars?
Yeah, go ahead, please. Yeah.
Okay, cool. So it turns out that dead stars seem to be the best particle accelerators, or at least the brightest sources. So novae, you have fast shocks in a dense environment. Core collapse supernovae in the first weeks to years, also even faster shocks in the same dense environment, and high mass X-ray binaries. So there you have the advantage that the plasma around the compact object is relativistic even before it enters the particle acceleration process. So it's easier to get to very high energies. So the plot here I'm showing is from the recent Hess paper in Science on SS433, and this red and yellow emission is the Hess result plotted on top of infrared and radio emission in the background. So RS Ophiuchi, this is recurrent novae that erupted in August 2021. So with Hess, we detected this actually on the first night. This was incredibly bright. It was by far the brightest Fermi detected nova. You can see this is the spectrum on 2 different nights, so the 9th and the 13th. And you can see that initially the Fermi was brighter on the first night than Hess, and then the spectrum gets harder. And although the Fermi emission is decreasing on the 4th night, and we interpreted this as basically we're seeing time-dependent acceleration. If you calculate the acceleration timescales, this is about what you would predict, that the very high energy emission increases after a couple of days. So we did a very simple model of this. So 4,500 kilometers per second shock expanding into the wind of a red giant with particle acceleration at the forward shock, and then hadronic emission from interaction with the red giant wind. We inferred pretty high acceleration efficiency from this model. It's probably too simplistic a model because presumably you have multiple shocks going on in the system, because you have this accretion disk around a white dwarf and some latitude dependence of the red giant wind, but this was a good start anyway. There is more detailed modeling required, I would say, but this was the first observation outside the solar system of time-dependent particle acceleration, as far as I know. Core collapse supernovae are even more extreme, and there have been suggestions that in the early months to years of supernova evolution, this is when you could get acceleration to the highest energy, maybe to PeV energies. And this is especially helped by the high density environment. So if you have stars that have very dense winds before they explode, for example, luminous blue variables, this helps. So in DIAS, we did some work on this, led by Robert Brose, using this RATPAC code for basically doing hydrodynamics, diffusive shock acceleration, and then models for transport and radiation. And we injected explosions into stellar winds, making different assumptions. And we found basically you can get the maximum energy of the particles over time, is plotted here. And it gets to about 600 TeV after 100 days for both of these cases. So this is a very dense wind from an LBV progenitor, and this is from a red supergiant progenitor. And not quite to a PeV, but pretty close. We also calculated the light curves and showed that actually this solid line is the TeV emission absorbed, and this here is the TeV emission unabsorbed. And so the emission for the first 100 days is actually pretty strongly absorbed. And so we calculated this for the type 2N case. For the type 2P case, very strongly absorbed. This here is a numerical artifact of the absorption interpolation scheme, but basically there's not much emission that you could detect for the first 100 days, and they're a lot fainter than these type 2N systems. So we're working on extending these models to where you have circumstellar shells that could be very dense, which are inferred from some of these type 2N supernova explosion light curves. And in that case, if you have a circumstellar shell that gets hit at about 100 days, then we're finding that you can actually get to a few PeV. And so I guess ask Robert Brose if you have more questions about this, or wait a couple of months and hopefully the paper will be out by then. But we can get very high energy emission, and it can be observed in the very local universe, so within a few megaparsecs. Then finally, so microquasars. So we had this really nice result on SS433. I think you should invite Laura to give a whole talk on this, because it's a really beautiful result. High mass X-ray binary, the massive star in a black hole and a relativistic jet, or mildly relativistic jet. And what we observed with Hess was basically emission from the two lobes of the jets, about 30 parsecs away from the star. And so this is the energy dependent emission you see at the highest energies. This coincides with these are X-ray contours here that you can see in green. So we interpreted this as basically this is a termination shock of the jet, and the particles are getting accelerated here to very high energies. And then we're seeing leptonic emission above 10 TeV. Then if you go to lower energy, the emission actually moves further down the jet. And if you go to the lowest energy, then it moves even further out, although it's quite a bit fainter. So this was the first observation of energy-dependent morphology in TeV emission of a jet. Really a fantastic result. And then the last thing I wanted to talk about was the gamma ray binary, so PSR 1259-63. Hess has observed this. Actually, we have quite a lot of papers on this, and we've observed all of the periastron passages, 2004, 2007, 11, 14, 17, and 2020. This is a cool system with a pulsar and an OE star in a very eccentric orbit, so that the OE star has a decretion disk around it, and the system is so eccentric that the pulsar passes through this decretion disk before and after periastron. And so these results were presented in 2023 by Charles Thorpe Morgan. This paper is now submitted, so hopefully it will be out pretty soon, the final results. So we detected this in 0.3 to 30 TeV or so. You can't see it in this. If you stack the whole spectra, it goes to 30 TeV. What we did for the first time with the 2020 periastron was we measured a statistically significant change in the spectral index, in that at the peak of the emission, the high flux state and TeVs, the spectrum was significantly softer than in the low flux state. It's quite difficult to interpret this system. I have to say, this was one of the most challenging parts of writing the paper. But yeah. Right, so I'm at the end. A quick summary. So I've taken you through wind bubbles, bioshocks. So around isolated stars, they're pretty weak non-thermal emitters. They might be good particle accelerators. They might contribute cosmic rays to the ISM, but we can't detect them really. Colliding wind binaries are a lot better because the densities, energy densities are higher. We've more chance to observe them. But actually, we don't see as many as I think we would have initially expected 20 years ago. And there are still some uncertainties in terms of the gamma-gamma absorption and the different cooling timescales in these systems. Star clusters, on the other hand, this is a very active topic at the moment. They're really bright high energy sources. They're effective accelerators, and we're getting really new results with current instruments. So I think the prospects for the next generation of high energy observatories are very good for making new discoveries in this area. And then at the end, so basically massive stars are brightest once they're dead. So I gave a very quick tour of novae, core collapse supernovae, high mass X-ray binaries, microquasars. I guess these will be topics of different talks in this series on their own. So thanks very much. Sorry for going a bit over time.
Thank you, Jonathan. That was really excellent. Thank you very much. I'm not able to see the screen, but I'm wondering if there are any questions. Maybe Julian or
I see you. Valenti has his hand up, I see.
All right, please go ahead.
Yeah, thank you. Thanks a lot, Jonathan. It was a very nice talk and you covered a lot of ground. I wanted to make a few comments about the first two parts because I wanted to add to, you mentioned this Del Palacio paper from 2018, but we have a very recent paper from last year by Martinez, Santiago and myself, in which we explore the radio emission from several bow shocks, and we try to make an analysis using some a little bit sophisticated semi-analytical models to try to understand better whether what we see is non-thermal or if it's non-thermal from the radio observations, whether we can infer something from the non-thermal properties. And in this regard, actually, I wanted to mention about, I think it's BD plus 43 something, which is extremely powerful star. And it's true that the radio source, it's relatively, like it's very spread. So it's not very, very bright, or it's not so easy to see and to study because you have such a huge source. It's very, very large. But, well, we were under the assumption that we more or less, we did some analysis trying to understand whether the spectral indexes were could be trusted. But in any case, when we were trying to infer the non-thermal energetics from this source, we even trying to be conservative, we got a very large amount of non-thermal energy only in electrons. In protons, it could be even larger. We were getting something like several percent easily of the total energetics available from the shocks going into non-thermal electrons. So I think that it was suggestive that the source is really very efficient accelerator, even if it's so big and apparently not so bright.
Okay.
I don't know.
Yeah.
You want to comment on that?
Yeah. I now that you say it, I'm aware of the paper. I didn't have time to actually read it carefully yet. I know Santiago sent a mail to my PhD student to see if she was interested to contribute to it, but at the time, she decided she was leaving astronomy, so she's learning machine learning to go and do something in industry, unfortunately.
Okay.
I mean, I think it's maybe I was a bit negative in my summary of the bow shocks that I mean, I think in the next 5 years, there's actually a lot of prospects for getting great new radio data with the LOFAR upgrades and BLA upgrades, and with the SKA in Meerkat and ASCAP. They're producing really beautiful large-scale images, and the new image reduction techniques seem to be much better for diffuse emission than the older techniques. So I think in the next 5 years, we will get quite big advances there, and we'll be able to say a lot more for sure about what the non-thermal emission from these objects.
Okay, I have just another brief comment about the binary colliding with binaries, because again with Santiago, he has these recent papers, one from last year, the other one is from a few years ago. One is about HD 93 something, which is a very young massive star binary system, and it's a very recent one, and he was studying the X-ray emission from around periastron passage, because it's not clear when periastron passage took place in the system. And then also from APEP, we have a paper from last year from APEP, and in both cases it was intriguing because there is evidence, not very high, very significant, but there is evidence of a power law potentially non-thermal component beyond, let's say, 10 kV, something like this. So if both sources are not bright there, I mean, it's not clear. It's not like Eta Carina, of course, but both of them are interesting in this sense of trying to feed data. It's good if you have an inverse Compton information for the inverse Compton model and also for the synchrotron component, right? So,
yep,
yeah.
Yep, absolutely. Yeah, okay. This is true. Thank you. I didn't mention this. Yeah, actually, I haven't read the paper on the HD 93 whatever. I actually saw it when I was preparing this talk, and I didn't have time to read it yet because I was looking for the paper on APEP, which, I mean, I think it's a bit weird that it's not very bright at high energies. But we also looked in Fermi a few years ago to see if we could see it, but there was really nothing there. And then the paper came out also doing a more detailed analysis showing that.
Yeah, well, actually, from Martín de Besa and Santiago del Palacio were talking about this, and now at present, I think the upper limits for the GeV emission are not too far from what model predicts. But let's see. I mean, of course, quite uncertain. Thank you.
Okay. Some more questions. I think Reshmi left already. Yes. Okay. So more questions, please. Hello.
Can I ask again, Felix?
Yeah, please go ahead.
Yes, but just so do you hear me, by the way?
Yep. Yeah, I hear you.
Okay, because Reshmi left, so I just realized now. Yes.
Okay.
Asking another question.
Okay. Thank you, Felix. So about this simulations you were doing for the bow shocks, I don't remember now where we got this, but we were trying to understand the contact discontinuity between the shock stellar wind and the shock ISM. And the simulations we found, and doing some analysis ourselves, we think that there is quite a lot of I think it was kind of evaporation of the shocked interstellar medium due to the hot shocked stellar wind. In your simulations of bow shocks, did you get something like that, or do you plan to take this into account? Because I think that there is some, well, let's say, conduction, some process which heats up and smooths the contact discontinuity very strongly, and it can affect actually the whole emission from the region, the thermal emission in particular, not only the dynamical structure.
Yeah, this is true. So there have been hydrodynamic models, including thermal conduction, which really broaden out the contact discontinuity very much because of this conduction process. And this actually gets rid of a lot of the instabilities that you see if you don't include it. No, so with these MHD models, we don't include thermal conduction. The argument is that the magnetic field, or the justification for that, is twofold. There's a practical one, that it increases the computational requirements by something like a factor of 10. So it's very expensive to include thermal conduction because it's a parabolic equation rather than hyperbolic. So the time stepping constraints become much more severe. So that's the practical reason. The physical reason is that the interstellar magnetic field should get sort of draped over the bow shock. So across most of the shock surface, the magnetic field should be, or across most of the contact discontinuity, the magnetic field should be parallel to the contact discontinuity, and this should strongly inhibit thermal conduction. Whether it does or not, I think needs to be solved by comparing with observations, which was why we just did the MHD models with high resolution, because they predict quite strong instability, which I think you don't see when you have this strong thermal conduction. And if you go back to zeta of Yuki, so you go back to zeta of Yuki here. I mean, to me, if you look closely at this WISE image, it looks like there's quite some strong turbulence here, assuming that this is the contact discontinuity. Although this is difficult to observe, and I think you really need the X-ray emission as well with greater sensitivity to say for sure.
Yeah, that's true. Magnetic field, it can inhibit significantly thermal conduction, but as you say, I mean, we need the different information from different sources to try to understand better the role of this process, because it can affect significantly the contact region and the properties of the shock interstellar medium in particular, which also produces thermal rate emission and so on. So.
Yeah. I mean, I did some work on this a while. The way that thermal conduction is implemented in these simulations is a bit unsatisfactory in that it also affects the properties of the shocks, which it really shouldn't do. And I think the implementation is not Galilean invariant as far as I can see. So like the thermal conduction changes the compression factor of the shock, which it really shouldn't, because it's a thermal process. But yeah, I think this is something sure needs more investigation.
Okay, thanks, Jonathan.
There are more questions? Jonathan, just a bit maybe not directly related to your talk, one question about the very massive stars in the 3 ultra compact clusters in the galactic center.
Mm-hmm.
They are result all this these giant stars in these objects, And what is difference, how they behave? They have the same behavior in other clusters, or they are there are some specifics of central galactic center region.
So you mean these three big clusters? So
Yes,
the
yes.
Arches clusters, the quintuplet one, and the one around Sagittarius A star.
Yes.
So I know about the Arches and the quintuplet cluster. They seem like perfectly normal star clusters, like, for example, NGC 3603 or how.
But this is much higher, right?
No, I mean they're slightly higher metallicity because they're at the center of the galaxy. So this means for a given mass, the stellar winds are going to be stronger. But if you look at the stellar populations, they're pretty similar to these other clusters.
Why is the so-called ultra compact ones? Do I understand correctly that there are only three, at least by definition, three only ultra compact clusters, which are free? All of them are in the galactic center. So you say this one is a more or less typical one. Is not.
You're talking about basically the stellar distribution, not in terms of mass, but in terms of radius from the center of the cluster.
Yeah, it's general.
Yeah.
I mean, this is this as an individual star is one thing. If they are packed in such extremely compact regions, there are changes or not. Do you see some?
I guess there should be changes in the binary
qualitative
fraction,
changes.
for example, in that the wide binaries all get disrupted. But
Well, binaries are everywhere the same binaries, but I mean, if they are the
no,
stars.
not really. I mean, if it's in a more compact cluster, then there will be more outside perturbations. So only the very close binaries will survive. And this will change then the late evolutionary stages of the stars. But I have to say I haven't looked into this.
Okay, thanks.
I didn't actually know that the clusters at the center of the galaxy are supposed to be more compact than these ones in the galactic plane.
Yes. So you have some more questions? So it seems no. So this today is a bit, we don't have many questions. So if so, thanks Jonathan again for the nice talk. And so Reshmi still is not here to announce. No, Reshmi is
No,
there.
I
but
think she is
she's
there.
not. No, but she's not available. I think she's driving. I understand. So
Okay.
just to announce next talk. So okay, Jonathan, thank you very much for this nice talk. See you in 2 weeks.
Great. Thanks,
Thank
Felix.
you.
See you.
Thank you.
Bye.
Bye.